Here's where we left off last time. We were talking about protection mechanisms uh, provided by the operating system. And we had been using the idea of the access matrix as a way of representing these, but really we wouldn't expect an operating system to record protection mechanisms this way, or at least to record protection information this way, mostly because it would be a huge data structure. We talked about this already, and I kind of hinted at it. We said every object, every file would need a whole column in this matrix, and every domain, everyone who could access stuff would need a whole row in this table. And that's going to be a huge data structure. So in practice, we represent this in a compressed way that lets us leave out entries that would otherwise be empty. Entries where a particular user or a particular domain shouldn't have access to that particular object. Or if we had an object that should be accessible by everybody, we can represent that in a compressed way. And I've listed the three standard ways of representing this at the bottom of this slide. Normally, this is represented as either an access list, a capability list, or we'll see in a moment, a lock and key mechanism. An access list is the idea that instead of storing protection information in one giant table, we'll store it in a list of who can access each object. So for each object, we'll record a list of who can access it along with what access rights they might have to it. So for this table, the one I've listed here, D1, if you're running in domain D1, you should be able to read from the object. Same thing for D2. For D3, we're pretending that's the owner of the object. An access list representation would kind of be a compressed way of representing the columns of this table. And the reason why that could be a much more efficient way of representing this is if a lot of the cells of this table are empty, if particular users running in particular domains don't have any access rights to the object, or if all users running in any domain have rights to access the object. Access list gives us a compressed way of representing that. So here for object O1, we just record who can access it. If there's a default access permission for any user who might want to access that, we can record that as a standard permission for whoever might access that. So you can think of the access list as a way of representing this table a column at a time, leaving out the entries that would otherwise be empty. And if we tried to represent this whole thing as a table, many of the cells would be empty, and this saves the storage for those. Another way you could go is representing the same table a row at a time, and that's what a capability list does. It represents for each domain what you can do if you're running in that domain. So it's kind of like storing the table a row at a time, but leaving out the empty representation or the empty cells of the table. So for the table I've drawn up at the top of this slide, D1 can read object O1, and if object O4 was a printer, maybe it can print to that. So the capability list for D1 would just include those two access rights. The fact that this cell D1 can't do anything with object O2, or it can't do anything with object O3, we would just leave that out of the capability list. And that would reduce the storage overhead for this. So backing up a slide, a couple of slides. An access list stores permission information for each object. A capability list stores permission information for each domain. There's one more way we could go, and this is something that you'll see in a lot of representations in practice, is there are some advantages to storing this, storing permission information associated with both the domain and the object. And lock and key gives us a mechanism for doing that. It keeps a list both for every object that can be accessed and for every domain that can access that object. And it connects these two together using typically a numeric key that says, if you're running in this domain, you can do these various operations on a particular object. So if we took the same access matrix and we're trying to represent it within an OS more efficiently, there are several ways we could carve this up into a lock and key mechanism. And I'm showing one way here. So if you look at the table up here, the access matrix, and again, the point is we want to be able to represent this more efficiently than what the access matrix, like if we stored this as a giant table, we want to represent this more efficiently than just implementing this as a giant two-dimensional array. For each object and each permission associated with that, each access right associated with that object, we could stamp that with a numeric identifier that says, if you have this, sorry, I said numeric identifier, and by that I kind of mean if you have this key, if a particular user or a particular domain can access, if they have this key, then they can access this object in this particular way. So here, in looking at this table up here, I've said, well, if you're running in domain D3, you're the owner of object O1, and you can write to object O2. So we could make a key that says you have both of those access rights. In domain D3, if you have, and I just made up a number for this, if you have the key numbered 25, that means you have both of these access rights. And for the two objects, O1 and O2, I said, if you have key 25, you're the owner of object O1, and if you have key 25, you can write to object O2. So it's kind of like what is shown in the top of this picture. If you have that key, then the two access rights that I put green circles around, you can exercise both of those on this object. That only represents part of this access matrix, but we can keep going. We could say, well, if you can print to the printer, then maybe there's an access right associated with that. And again, I just made up a number for this. Maybe if you've got key number 9,000, that means you can print to the printer. And looking at the table up here, D1, D3, and D4 should be able to print to the printer. So if you can do that, I could give each of them a copy of that key. And then when the operating system is trying to decide whether or not they should be able to exercise that access right, whether they should be able to print to the printer or not, it can just check and make sure they have a key that matches that access right for this particular object. And we could keep going. Looking at the table, I noticed that object O2 can be written by processes running in domain D2 or D3. And if I wanted to make sure they had that access right, I could give them a key. I could give D2 and D3 a key that let them write to that object. Down at the bottom, you'll notice for if you're running in domain D3, you've kind of got two keys that let you write to that object, and that's okay. If you've got key number 25, that lets you write to object O2. And again, I just made up this number. If you've got key number 5566, that also lets you write to that object. And that's okay for a lock and key mechanism. There might be multiple keys that let a process running in a particular domain access or exercise a particular right on an object. That's okay. One reason I say you might want to do that is later when we talk about revoking rights, if you got multiple reasons or multiple keys that let you exercise a particular right, the OS or users ought to be able to revoke some of those keys. But if you still have keys that let you access a particular object, even if some of those keys have been revoked, you should still be able to exercise rights based on older keys. Let me try and say that again. We can give out keys to domains and then later revoke some of those keys. But if there are other keys that let you still access those objects, then you should still be able to exercise those rights. I've got a later slide that hopefully tries to make this make more sense. All right, so continuing with this table, I'm kind of carving up this table into multiple keys that give different domains access rights to the objects in this table. If we continued this process, and kind of a thing to notice here is for a lock and key mechanism, there are multiple ways of taking a collection of objects and assigning keys to access rights to those objects, so that the access rights shown in this table are still respected, but I've got some mechanism for granting new domains access rights or revoking those access rights later. So for access list and for capability lists, there was typically just one way to assign access rights, but for a lock and key mechanism, there are multiple ways to associate keys with particular access rights. And all three of these mechanisms are ways of representing this, what would in practice be a giant 2D table, for representing that in a small form that is easy-ish to store and typically easy to answer the question that the OS has to answer all the time. And that is, if a particular process running in a particular domain tries to do something with an object, should the OS permit that or not? And that's the kind of thing that I'm talking about on these next slides. Given the three representations that typically show up, for an access list, if a process running a particular domain tries to open a file for reading, if it tries to access an object with particular permissions, the OS needs to be able to decide that efficiently. Same thing for all the other representations. Since access rights store permissions with each object, all we have to do is, all the OS has to do is look up whether or not the domain a process is running in has the access right it's trying to exercise. So is it permitted to open a file for reading? Is it permitted to open a file for writing? And access list makes that fairly easy to answer the question, can the OS, or sorry, can a particular process running in a particular domain access an object with particular permissions with the way it's trying to access this? It makes it harder to answer questions like, if you had a particular domain, what kinds of things can you do in that domain? Because that information is stored, spread across every object on the system. A capability list makes those kinds of questions easy. If you want to know what you can do if you're running in a particular domain, you've already got a list that does that. But if you wanted to know what kinds of objects you can, or sorry, if you wanted to know who can access a particular object, then with a capability list representation, that's a little more difficult to do. You would have to look at every domain and see who can access a particular object. The mechanism we just talked about, a lock and key mechanism, is maybe even harder to answer questions about. If a particular process tries to open a file, or if it tries to access a particular object, what is it permitted to do? Because we have to look at two lists. We have to look at all the keys associated with a particular domain, and we have to look at all the keys associated with a particular object. And if any of those keys permit a process running in that domain to access that object, then the OS permits that access. If there are no keys that let it do that, then the operating system should deny that particular operation. So, if you try to open a file for writing and you didn't have access permissions for that, if you had a lock and key mechanism, then the OS would have to look and see if you had any key that permitted you to write to that object. So lock and key can give us, I tried to make the point, it can give us a lot of flexibility for assigning keys to particular domains. And if we plan ahead, it can give us a lot of ways, a lot of flexibility in revoking access rights in the future, kind of like the name suggests. If we decide that a particular key should let you access an object for a while, and then later, sorry, I pick university related examples for this, but if we had a key that let students access a particular lab for a part of a semester, and then later if we decided they shouldn't be able to access that anymore, then we could revoke access using that key. Any students who only had that key wouldn't be able to access that lab anymore. But students who also had other keys that let them access that, maybe because they were part of a research group that let them access that lab, they would still be able to access it. Revoking access to resources can be easy under a lock and key mechanism, as long as we plan ahead, as long as we make sure that that when a particular key should not grant that access anymore, that we can revoke that key, we can mark it as not giving us access, giving particular users or particular domains access to that object anymore. We can revoke access for anyone who had that particular key. But again, like I said a couple of times, that requires planning ahead. If you look at the access permissions supported by sorry, I accidentally pressed a key there. If you look at the access permissions supported by a typical Unix system, it provides a mechanism for doing this, but it simplifies, for the OS, it simplifies looking up a particular key. So it tries to make this efficient, and it tries to make it so that it's easy to store permission informations for any object. if I had to describe the permission mechanism supported by a standard Unix file system, it is mostly an access list mechanism with a little bit of lock and key provided to give us flexibility. Every file, and we've kind of seen this on other examples we've used, every shared memory segment you create, every named semaphore you create, gets stamped with a small amount of permission information that I've shown over here on the right. Every one of these objects gets an owner, which is a small number that indicates who made that thing. So if you create a file, then by default, you're the owner of that file. You get to decide who can access that file. It also gets a small number of bits that say what you can do with that file, or not just you, but any user can do with that file. And that's what I mean by these mode bits here. Every object you create also gets a group user associated with it. And that's kind of what we're going to talk about next. That is a simple Unix mechanism for deciding what users can access that object, or it is a simple lock and key mechanism for deciding who can do what with that particular object. And that's what I've tried to illustrate on this next slide. For every object, and when I say object, I mean a file or a chunk of shared memory or a named semaphore that you create, where you might want to control what processes can use that thing and what they can do with that thing. There are 9 bits that are associated with that object that decide who can access that object in various ways. And that's what I've tried to list here at the bottom. Of those 9 bits, there are 3 of them that decide what the owner of that object can do. So if you're the owner of that object, can you read that thing if it's a file? Can you write to that thing? Can you change its contents? If that's a file, can you run it as if it's a program? And there are 3 more bits that decide if you're maybe not the owner of that object, but if you're in the same group as the creator of that object, as the owner of that object. Can you read it? Can you write it? Can you execute it? And otherwise, if you're neither of those, can you read that thing? Can you write to that thing? Can you execute that thing? Down here at the bottom, I've listed how each of those bits are interpreted by the OS, or what they're used for if you're trying to access the object. I kind of describe these as if you were trying to access a particular file, but all of these bits are associated with other things in the operating system, including things like directories and semaphores or shared memory segments. And if they're not plain old files, the way these bits are interpreted depends on what objects they are. So if you have a directory, the read bit still exists. It's still associated with that directory, as we'll see a couple of lectures from now. But if you're trying to access a directory, and when I say a directory, I mean a part of the file system that might contain multiple files. The same bit says whether or not the read bit says whether or not you can see a directory listing. The write bit says whether or not you can change what's in that directory, and that would normally mean, can you add or remove files from the directory? And the execute bit, there for a directory, I don't know if execute makes sense or not, but they use that same bit to indicate whether or not you can see attributes for that, for files in that directory. So can you see who owns them? Can you look in subdirectories for those? And this is kind of what I've tried to hint at earlier for typical permissions systems. They support a limited number of mechanisms, and those get used, those get interpreted differently depending upon what kind of object they're associated with. So like I've listed over here for a plain old file, these bits mean, can you read from what's in that file? Can you write? Can you change what's in that file? Can you, if that file was a program, can you execute it or not? And if that thing was not a plain old file, if it was a directory, if it was part of the file system that contained or that represented other files, then these bubbles over here are what are how those same bits are interpreted for something that may not be a plain old file with just a sequence of bytes in it. So here I've tried to list for a Unix system, every file has a owner. That is simplified by every file has a numeric ID that says who owns that file, and every user has a numeric ID. And if your ID matches what's on that file, then you're the owner of that file. Same thing for the group information. Every file has a group owner. Backing up a slide, I probably did a poor job describing this, but every file has a group associated with it. And if you're part of that group, that determines what you can do with that file. If you're not, if you're neither the owner nor a part of the group for the file, then these, let me try and say this again and say it accurately. If you're the owner of the file, these first 3 bits decide what you can do with that file or directory. Can you read it? Can you modify what's in that file? Can you change what's in that file? If you're not the owner of the file, but you're part of the group associated with that file, can you change what's in that file? Can you read what's in that file? Can you change? Can you execute that? And otherwise, if you're neither of those, what are you permitted to do? Can you read the file? Can you write it? Can you execute it? And that's what I'm trying to say here on this slide. These 9 bits associated with the permission of the file is a kind of a baseline for Unix permissions for accessing files or directories. For files, that's kind of what I said a moment ago, backing up a slide. For directories, for parts of your file system that might contain other files, then these bubbles over here list what you can do with subdirectories, what you can do with files that are contained in directories. This middle part, the group mechanism, you can think of that as a simple lock and key mechanism, partly because users or domains can be part of multiple groups. So if you're a user on a Unix system, you might be a member of more than one group. And as long as you're a member of a group that gives you access to a file or directory, then you're permitted to access that file or directory. For a Unix system, this simplifies file access a little bit because every file only has one group owner. But if you try to access a file The operating system just needs to look and see if you have a group membership that lets you access the file in that particular way. For instance, if you try to read from a file, the group ownership might say that, well, normal users can't read from this file. They can't look at what's in this file. But if you're a member of a group that is permitted to read from that file, then the operating system will let you open that file for reading. The point I'm trying to make is this is simplified because every file just has one group associated with it. And if you try to access the file in a particular way, the operating system just needs to decide, are you the owner of that file? If so, then these first 3 bits determine whether you can read or write or execute that file. If you're not the owner of the file, then the next 3 bits tell us whether you can read or write or execute that file, provided you're a member of the group that is the group that owns that file, provided you're part of the group that that file is stamped with. And otherwise, if you're neither the owner nor a member of the group that owns that file, then these last 3 bits say what you can do with that file. And again, the advantage of this is it's a small amount of storage for permissions information for each object that the operating system has to keep up with. And it makes it computationally efficient to answer permissions questions. And that's kind of what I tried to say a moment ago. If you're the owner of the file, these 3 bits say what you can do with the file. If you're a member of the group that the file is stamped with, these next 3 bits say what you can do with the file. Otherwise, if you're neither of those, these last 3 bits say whether you can read the file, whether you can write the file, or whether you can execute that file as a program. You probably already know some of this stuff. There are standard shell commands for letting you look at and change the permissions associated with file. If you run this last command, ls dash, I know that looks kind of like a 1, but that's an L. If you run ls-l on a file, it'll tell you the permissions associated with that file. It'll tell you these 9 bits we're talking about. And if you're the owner of a file, you can go in and change these bits. Chmod, C-H-M-O-D, lets you specify the permissions associated with the file as an octal number. And this is, for me, this is one reason it's handy to know octal. The owner bits, the group bits, and the user bits, or the other bits, are 3 bits. And octal makes it easy to specify bits in groups of 3. So for Chmod, it normally expects, if you run Chmod to change the permissions, the mode bits associated with file, then you can specify who can do what with that file by specifying each of these as an octal value. So Chmod, like I'm showing at the top of this slide, Chmod 750 would say, if you're the owner of the file, then your permissions are 7, which in octal would be 111. It would specify 3 bits, so that would permit you to read or write or execute that file. If you're not the owner, but you're a member of the group associated with the file, then this 5 in the middle would say, You're permitted to read and write, sorry, you're permitted to read that file and execute it, but not write it. And the 0 in the lowest order digit would indicate that you're not permitted to do anything with that file. The 3 low order bits are all 0. And maybe looking at this line down at the bottom would make that more clear. If you specified permissions as octal digits, then the lowest order digit would determine these 3 lowest order bits. The next digit, this 5, would determine the next 3 digits, sorry, the next 3 bits. And the 7, the highest order octal digit, would determine the highest order bits. And for a while, this was a handy reason to know octal. Chmod has been enhanced since then, so you don't really need to know octal to change permissions bits on a file anymore. It provides a more flexible mechanism for letting you add read and write permissions. So like I'm trying to show here in the middle, chmod O+R would mean give any other user access to read this object. So it has a more expressive syntax now. These are all shell commands that let you change these first two, and kind of this last two, or sorry, this last one lets you look at who owns a file and look at the permissions bits associated with that file. This second to last one lets you change the owner of a file on the Unix machine. All of these are shell commands, meaning that they're just programs like you and I could write. They may run with different permissions, the programs that we write, but internally they must make operating system calls. They must make system calls to ask the OS to change permissions associated with files. And this is what's happening internally. If you call chmod, or if you call this guy, I don't have a good pronunciation for this, but if you try to change the owner of a particular file, there are system calls that let you specify that. And these are at least 3 of them that you can use. And these are things that are used internally by the commands that we just talked about when you change permissions on a file. Chmod is opening that file, and internally it's calling fchmod, a system call that expects a file descriptor as the first parameter, and whatever mode you want to change the permissions of that file to as the next parameter. The next call is for changing the owner of a file, if you wanted to give away ownership of a file. And the last one, I don't know if ls-l really uses this internally, but we've talked about this maybe a couple of times this semester and in examples. The stat call shows up in many forms, and it'll let you see the permissions associated with a file. If you've got a file that you've already opened and you've got a file descriptor for it, so a small integer associated with that file, fstat will tell you information about that file. You just have to give it the file descriptor, the integer that you got when you opened the file, and a pointer to a struct, and it'll fill in that struct with all the information we talked about: who owns the file, what group ownership is associated with that file, the permissions bits associated with that file, and a bunch of other stuff that we haven't talked about. But this is a standard way of getting information about a particular file. So Unix, at least if you were implementing a Unix system, this this mechanism makes it really easy to store permissions information. Every file has, and I probably should have done a better job of this way back here when I described this. Every file has an owner, and that would apply to other things that permissions have to be applied to. Everything has an owner. Everything has a group ownership associated with it. And everything has these 9 permissions bits associated with it. What can the owner of the thing do? What can a member of the group for that thing do? What can other users do if they're neither the owner of the thing nor a member of the group associated with that thing? And when I say thing, I mean file or semaphore or shared memory segment. But 9 bits for the mode bits is a weird number to have to store. Depending upon how you stored that, you'd probably have some extra bits, and at least on a Unix system, those extra bits are used. Historically, they've been used for different things, but I normally describe this as for every file, there are 3 additional bits that describe what users can do with that thing. And that's what I've listed here. The permissions bits associated with the file normally include 3 additional bits that, that specify what other users can do with that file or object. And I've listed these here. So on past the bits that say what normal users or members of the group or the owner of the file can do, there are 3 bits called normally the set UID bit, the set GID bit, and the sticky bit for that object. Let me try to describe these real fast. The set UID bit says if that is set to 1. If it's set to 0, it doesn't do anything. But if it's set to 1, it tells the operating system, when you run this program, run it as if you're a member of the, as if you were the owner of this file. This is a mechanism for selectively giving away elevated privileges when a user runs a program that's marked with a set UID bit. I accidentally tried to say this a moment ago, but the set GID bit, the next one, says the same kind of thing, but just for the group ownership bit. If this is a program and its set GID bit is 1, if it's non-zero, then when a user runs this program, they will temporarily, just for the duration of that program, they'll be given group permissions of the file rather than their own group permissions. Let's talk about those 2 for just a moment. The next one, well, I'll go ahead and say it, although it is probably the least important nowadays. The sticky bit, the next bit in the permissions, is really a hint to the operating system that says, if anyone runs this program, even after they've quit running this program, keep it in memory because someone else might try and run it later. This is kind of a performance hint for the OS that helps it decide what to keep in memory and what to throw out. This was probably more important in the early days of operating systems, where where memory might have been more scarce and the OS had to make decisions about what to keep in memory and what to throw out. For programs that were going to be run by multiple users, like maybe a compiler or maybe a text editor, we could go in and set the sticky bit to give the OS a hint to say, why don't you keep this in memory? On modern systems, memory is probably less scarce, and the operating system is already making pretty good decisions about what to keep in memory and what to throw out. This bit is less important than it used to be. And modern operating systems have used this bit to store other things, or at least have used this bit to indicate other things. But at least historically, this next bit was used as a hint to the operating system. These remaining two are still used by Unix operating systems to keep up with what I talked about a moment ago. The setuid bit is a simple mechanism to let us mark programs where if you run this program, at least while you're running it, you get the permissions of whoever owns that program. And like I said, for the setgid bit, while you're running this program, you temporarily get permissions of whatever group is associated with this. And this is at least on a Unix machine or Unix-like machine, this is a mechanism for temporarily letting you switch domains. If you're running a program and it calls a program and the setuid, it invokes another program and the setuid bit is set on that program, while that other program is running, you get the permissions of that other program. Same thing with setgid. If you run another program and its setgid bit is non-zero, if it's 1, then while you're running that other program, you get to execute as if you're a member of that group. So this, we'll see this in a couple of slides. This gives us a way of temporarily letting a program switch domains. It can run other programs that give it elevated or reduced privileges based on these two bits. I've talked a lot. Are there any questions before I can try to go on? All right, so I hope people are there. And I kind of hinted at this next idea that as processes are running, maybe they shouldn't have the same privileges throughout their execution. Maybe for some stages of their execution, they need ability to access more files, and for later stages of their execution or for other stages of their execution, maybe they need fewer permissions for that. We've got a term for this, at least for thinking about this. And the idea is the principle of least privilege. It's a simple idea, but I feel like it's easy to get this wrong when you're trying to think about how to configure a system or what a particular process should do. Principle of least privilege says when a process is running, it should have only the permissions that it needs to do what it is expected to do, which seems like an extremely obvious idea. But like I said, if we apply this to a particular situation, I think it's easy to get this wrong. Let's pretend I was working with a coworker. Let's pretend I was working with a colleague. And we both needed to use some of the same files. Maybe we need to be able to put things in those files and serve them to other users out there on the internet. The thing that makes this maybe a little complicated is I need to be able to read and write those files, and whoever I'm working with needs to be able to read and write those files. So we got a couple of ways we could provide this. Since we both need to be able to access those files, And we need to be able to provide those to other users out there on the internet. We could possibly mark them as readable by everyone on the system. That would let any user on the system access those files, but it would potentially give away a lot more permissions than we wanted. Maybe we'll only be, maybe we will only want to serve copies of those files to other users. And we don't want other users to be able to modify those files. So making those files accessible to everyone on the system might give away a lot more permissions than we want. We could get to this from another direction. We could say, well, maybe we need to grant whatever server is using or is granting access to these files. Maybe we need to be able to grant that additional privileges. So we could run a server that gave away access to these files, and we could just run that server with administrator privileges. And that would let it access my files. It would let us access other files on the user. But I think that would violate the principle of least privilege, because that server running with privileges that are that high could access any files on the system. Maybe a better way to do this would be using that group mechanism that we talked about. Maybe I could take any files that need to be accessed by me and by my colleague, and maybe we could make up a new group associated with that project. And then any files that we both need to access could be stamped with that group, and then we could both access them as long as we were both members of that group. And any other processes like a web server or other users that need to be able to look at those files could access them without having to give away access to all of those files to everyone. So I don't know if I did a good job of this, but in talking about the idea of the principle of least privilege, I tried to talk about first an example where we would give away way more privileges than we wanted. And then I tried to talk about an example where maybe we could give a process way more privileges than it needed. And then I tried to point back to what we said at the start of talking about this. And that is for protection mechanism, it's good for the OS to provide us mechanisms that are flexible enough to let us choose policies that are appropriate for our domain without forcing us to give away way more permissions than we need. Questions before we try to move on? I got a couple of more things to say about protection mechanisms.
I have a question. Can you hear me?
Sure. Yeah, I can.
How would we go about adding access to different domains if when the file's created, it already has a group associated with it?
So for this example, I've got an easy answer, but it might be harder for other examples. Like if I was working with a colleague and I said, for any files that we make that are associated with this project, we'll stamp them with a particular group ownership. We could just agree to do that. And then like if I made a directory, any files that I put in that directory, I could stamp those with group ownership that let me or my colleague answer them. And even though I didn't really talk about this in the previous slides, there are things provided by the OS that make that easier to do. So you can stamp directories and say anything made in this directory, unless you say otherwise, it'll have these group permissions associated with it.
Okay, thank you.
Sorry, I'm hesitating because I don't know if I've really answered your question. But there are ways of um, making it so that you can share resources on a particular system. And the OS tries to respect your decisions on that. In other cases, like if you were both working on a Git repo, then each owner, each user that checked out a copy of that Git repo would have their own copy of it. But if they made changes and tried to check those changes in, then wherever that repo was hosted would decide if they're permitted to do that or not. Like I said, I'm worried I didn't really answer your question. But at least as far as permissions on a particular OS, I tried to make that make sense.
Gotcha. Yeah, that was helpful.
Other questions? All right. One reason I hesitated here is because I was lying to you a little bit, or at least I was trying to simplify things a little bit. If a process is running, and I hinted at this before, it may temporarily need more permissions, and then later, if you're running less trusted code, you might not want it to be able to access particular things. You might not want it to have access to all of your access rights throughout the execution of the process. So to do a good job at this, it seems like we need a mechanism that would let a process dynamically change its permissions, change its domain as it was running. We talked about that earlier when we were looking at the access matrix. We said, well, it might be handy to be able to switch domains you're running in, but only temporarily, only when you need to do certain things that required additional permissions. Or I guess said the other way around, if you're running code that was less trusted, you might want it to have access to fewer permissions while it was running that. So really, we would like processes that can change, or we'd like an OS that can enforce different permissions as processes run. And that is going to require something else. So far, we've assumed that a process, as it was running, it could make system calls whenever it needed to, and the OS would decide what to do based on that. But now we're kind of talking about if we wanted, to sneak in the two terms in the middle, dynamic association of a protection domain with the process. That means what we're talking about right now. As a process runs, it can temporarily, at least it'd be nice if the OS could let it temporarily have elevated permissions. And then later it might have reduced permissions as it ran. And we talked a little bit about how at least the Unix file system gives us a little bit of a way of doing that. The set UID and set GID bit let us at least let a program invoke other programs. And then if you run some other program with a set UID bit, then while you're running that program, you temporarily get the permissions of whoever owns that program. Same idea for the set GID bit. But to do a good job of this, we might need a mechanism that lets us do this throughout the code. And there are language-based mechanisms that at least give us some way of doing this. If within a program, we need to be able to decide, if you're running code within this function, are you permitted to do this? If you're running code in some other function, what are you permitted to do? So we need at least to do a decent job of this. It seems like we need some mechanism for checking permission within the execution of our program. And you already know at least a little bit about this. whether you're running in Java or C and C++. The reason I mention those is even if you came up through Java, a lot of the mechanisms for permissions for protection are inherited from C and C++. So the idea of having functions in an object that are marked as protected or private or public or package. Sorry, I'm trying to think of all the ones in Java. Those are language-based mechanisms that decide who can call that particular method, and to an extent what can happen within that mechanism. Do those provide the kind of things that we're talking about? Do those let us write programs where we can decide what things are safe to do and what things are not? In C or C++, I'll go ahead and say, as you probably can guess from looking at those languages, that the compiler doesn't offer you a whole lot of guarantees about that. In C++, you can mark functions in a class. So kind of like Java, in C or C++, you can, or sorry, in C++, you can put functions inside a class and you can mark them as public or private or protected. But if someone wants to cheat, they can get around those mechanisms because, as you remember from C class, from the C course, if you've got access to the memory where an object is stored, you can look at what is stored inside that object, even if the compiler tries to keep you from doing that, even if the programmer tries to keep you from doing that. Java has some more secure mechanisms for that, because if you write a class in Java, even if you try to cheat, even if you tried to write your own Java bytecode to sneak around and look at the contents of a class, then the JVM, the Java execution environment, does bytecode verification on whatever you're trying to run, and it tries to make sure, using a lot of clever techniques, it tries to make sure that you don't sneak around the protection mechanisms provided by Java. So things like public, private, protected are a lot more secure in Java than they are in a language like C++. But I want to say those mechanisms alone are not nearly enough to do what we're talking about. And I've just picked an example for this. Whenever you type commands at the shell, it records a command history, and we benefit from this. Like if I type a command to run the compiler or something like that, and then later I need to type the same command, instead of having to type it again, I depend on a command history that lets me look back at previous commands that I've typed and access those and even edit them without having to retype them, even across sessions. If I log in and then log out and then later log in again, my shell keeps a history of every command I typed. And I guess if I'm just running the compiler, someone else having access to that history might not be a big deal. But if I'm typing in commands that could be sensitive, maybe commands that have passwords in them, I wouldn't want other untrusted users from being able to access those. But the public-private protected mechanism offered by Java doesn't care about that level of detail. If you look at the Java API and you look at opening a file or opening a scanner to read what's in that file, all of those methods are protected, which means Java doesn't care about who calls those methods. So if I was having to worry about even in a language like Java, permitting some code to access that data and rejecting that for other pieces of code, I would need a lot more than just public, private, protected to mark that. And that's kind of what I'm trying to say at the top of this slide. Making a scanner, opening a file and giving it to a scanner, those are all public methods. Java isn't designed to reject potentially untrusted code if it tries to access files on a system that maybe I wouldn't want it to access. Java still has a mechanism for doing this. It's just a slightly more complicated mechanism. And it kind of reflects what I said a moment ago. If you're running a program, you may have pieces of code that are trusted and other pieces of code that are less trusted. If you're running a program like a game or something that you downloaded, then not every piece of that code should be able to access every public method offered by Java. Java includes, or in general, for language-based protection, what code should be able to invoke particular methods depends on where that code came from. And that's what I'm trying to illustrate in this picture. If you're running a program in practice, you might have run a program that called some methods, that called some other methods. I'm sorry, I'm pointing with my mouse pointer here, that called some other methods, that called some other methods. And those methods might do things that you would only want trusted code to do. For instance, they might open files on your file system. They might potentially give away secret information. When you call a function like this, you need to be able to decide, should we let that file be open? Should we let that potentially protected data be accessed by potentially untrusted code? Now I'll make the point, well, you don't want, if you downloaded some files that were less trusted, like if you're trying to play a game or you were trying to run some code that was hosted by a web server, you probably don't want to completely prevent it from accessing files. But you want to, at least within Java, you want to be able to decide what files it can or cannot access. So within Java, they provide a mechanism for whenever you're trying to do some potentially protected operation, something that not arbitrary code should be able to do. It looks for what code is invoking that. And that's what I'm trying to illustrate in this picture. It looks for, well, for a protected operation, for doing something that could potentially give away secret information. Java provides a way of saying, well, who asked me to do this? And that is essentially doing stack inspection. Who called the function that would do this? And that might require saying, well, this function called this potentially protected subroutine, this potentially protected mechanism. Who asked it to be called? Who asked that function to be called? So Java, for protected information, it provides a mechanism for looking up the subroutine call stack, the method call stack, and trying to decide who asked for this operation to be called. And within Java, it takes some additional code. So this is not automatic, but it provides a way of marking subroutines and inspecting who called those subroutines to try to decide whether or not some potentially dangerous operation should be permitted or not. This is built into the Java language, but like I said, if you're writing code that's going to use this, or you're writing code that's going to check this, you have to write that code yourself. When you're about to call a subroutine that could include some protected access, like accessing files on the file system, there's a way of calling that subroutine and marking the stack to say that to essentially guarantee that that subroutine isn't going to be asked to do anything that violates the permissions you want, that essentially takes responsibility for the operation you're about to do. Within that subroutine, if you're about to open a file that you wouldn't want untrusted code to be able to open, there's a way of checking to see if there is trusted code that is willing to take responsibility for that operation. And that's what I've tried to illustrate in this picture. This lets Java, languages like Java, provide libraries or provide frameworks where even untrusted code can do things like open files on your local file system, can read what's in those files, but only under special circumstances. So if you've got some untrusted code, and I think I probably skipped this earlier, but you've got some code running in your JVM that potentially got downloaded from the internet. So within a JVM, it assigns different permissions to files that might have come off of your local hard drive versus files that potentially got downloaded from the internet as your program was running. For files that came from your local hard drive that are part of your JVM installation, those are more trusted. From files that got downloaded from classes that got downloaded as a program was running, those are less trusted. And that's what I mean by this yellow box here. So if you had a piece of code that ran some code that was less trusted, and let's say it wanted to use a library that provided it access to your local file system, but only under special circumstances, like maybe to access some of its configuration files. Then within that library, Java provides a mechanism that lets you, backing up a slide, that lets you use what we talked about right here. You can have a piece of that library that says, well, even though I'm about to access a file, I'm about to access something that could arbitrarily, sorry, that could be any file on the file system, as long as they're going through me, then they should only be accessing part of their configuration. They're not accessing files that could potentially give away information that should be secure. Java provides a mechanism that lets trusted code take responsibility for potentially protected method calls. And then later, if that piece of code calls another piece of code that calls another piece of code that asks it to open potentially to open files that we might want to be secure, as long as there's a piece of trusted code that's willing to take responsibility for that, then within limited types of access, we can give away access to things we might want to secure to untrusted code, but only if it goes through protected libraries, only if it goes if only if it accesses that via APIs that we trust. And that's, it's probably longer than I meant for this to take, but that lets a language like Java give away access to protected information, but only if that access is given via protected code. Sorry, there was some hesitation at the end, but this gets us to the end of talking about protection, which is mostly about mechanisms for giving away access to, for really telling the OS how it should and should not permit access to resources. Our remaining topic is talking about security. What if we had users or processes that were deliberately trying to get around these protection mechanisms? How could we try to prevent them from doing that? How could we detect if they tried to do that? And that's really the topic of security. That's the next one we'll talk about. But we're out of time for today. So we'll call it a day now, and we'll pick this up at the start of next week. Thanks for your attention. I am going to stop recording